Okay, so we are going to start. Okay, you can see the screen, huh?
Yes, sir.
Yes, sir.
Okay, so last class we saw the method of the uh, epsilon cutting method. Okay, so this class we look at this weighted sum method for multi-objective optimization. So this is a very common method used for multi-objective optimization. So what we do here is that we minimize the weighted sum of the objective functions. So minimize sigma wi fi. Okay, where I equal to k is the I equal to 1 to k is the number of objective functions, and the sum of the weights should be equal to 1. Okay, so suppose we have two objective functions, f1 and f2. Okay, so this means you have to minimize w1 f1 plus w2 f2. Okay, so two objective functions are added to become a single objective function. Okay, so then you can use the single objective function optimization algorithms like Cauchy's methods or Hutcher-Reeves methods or sequential quadratic programming. So those types can be used after the multi-objective problem is converted to single objective. Okay, but some conditions are there before you use this W1 F1 plus W2 F2. So first is that the sum of the weights must be equal to 1. Okay, so the W1 can be 0.1, W2 can be 0.9, W1 can be 0.2, W2 can be 0.8, and W1 can be 0.9, this can be 0.1. Okay. So W1 plus W2 must be equal to 1. That is the first condition. Second condition is that the objective function must be of the same scale. So they must be normalized. Okay, so this F1 may range in values from 0 to 10,000. And F2 may range in value from 0 to 1. So when you add this W1 F1 plus W2 F2, then this W2 F2 will become negligible when compared to W1 F1. So to avoid that, you have to normalize both these objective functions to the same range. So F1 must vary from 0 to 1. F2 also should vary from 0 to 1, roughly. So that process is called normalization. Or F1 must vary from 0 to 100. F2 should also vary from 0 to 100. That process is called normalizing. Okay. So in such a case, the theorem says that for positive values of weights, that is, all this will be positive. For positive values of weight and for convex feasible regions, the optimal solution of the weighted problem gives a point on the Pareto optimal curve. So if you take the Pareto curve, each combination of weight will give 1 point on the Pareto curve, like this. And somewhere near the utopia point, the weights may be roughly 0.5, 0.5. Okay, so if you put 0.5 into F1 plus 0.5 into F2 and minimize the objective function, and if the optimization problem is a convex problem, then you will get a point somewhere in the middle of the Pareto front and close to the utopia point. So that is why most engineers will use these weights 0.5, 0.5. Okay, then by using different weights, we get different points on the Pareto form. So that is what is shown here. So how do we normalize the objective function? Various type of rules are there. First is you can divide the objective function with the mean value of that objective function within the visible range. So ith objective function is fi of x, because that is divided by mean value of objective function within the visible range. So mean value is obtained approximately by adding the maximum value of the objective function in the feasible range plus the minimum value of objective function in the feasible range divided by 2. Then to normalize in the range from 0 to 1, you can use this another equation. So this is the expression of the objective function minus minimum value of objective function in the feasible range divided by difference between maximum and minimum value of objective function within the feasible range. But to do that, we have to find the individual maxima and minima of each objective function. So we have to find f1 min, f1 max, and similarly f2 min, f2 max. Only then you can do the normalization. So we'll just look at an example how to normalize the objective function of the previous linear programming problem. So there f1 was 4x minus y, f2 was minus 0.5x plus y, and these are some constraints. So how do you normalize them? Okay. So first we'll see how to normalize the first objective function. That is f1, that is 4x minus 5. So we already found in the graphical method that maximum value of f1 is 16, minimum value of f1 is minus 1. Okay, so normalized value of objective function is, this is actually f1 of xy divided by maximum value plus minimum value by 2. So 16 minus 1 by 2. So 4x minus y divided by 7.5. So 7.5 is the normalizing factor. Okay. Then similarly for f2. How do you normalize f2? This is the expression for f2. This is the maximum value of f2. This is the minimum value of f2. And then it is divided by 2. So this is the normalizing factor of the second objective function. Okay. Okay, so the weighted sum method is not so simple as it seems. So because first of all, you have to do the normalization, and to do the normalization, you have to find the maxima and minima of each objective function. So many people don't normalize the objective function, and without that, they will write W1 F1 plus W2 F2. Actually, they should write W1 F1 bar plus W2 F2 bar, where F1 bar is the normalized objective function F1, F2 bar is the normalized objective function F2. The next we go to
Yes, sir. Can you go to the previous slide, sir?
Oh, this one. Oh.
Here we have.
Yeah.
So we have tried this method only. Okay.
No, next slide. Workout program. Problem.
No.
Are we finding the minimum and maximum F1 max, F1 min through graphical representation?
Yeah, you have to find. You have to find. You have to do single objective minimization of F1, single objective maximization of F1. Then you have to do single objective minimization of F2, single objective maximization of F2. Those. Okay, then another method you can do is that if this is the feasible region, you can sample some 10 or 20 points and find the average of all those points. So that can be used instead of this. Okay. So you can sample 10 or 20 points randomly in the feasible region and find the average of it. Okay. Okay, next is called goal programming, which is a practical approach to multi-objective optimization. And here the objective function are given some targets or goals to attain, and then they become constraints. And the deviations from the goal are represented by slack variables, which are minimized. And by looking at the solved slack variables, we can say whether the goal is attained or not. If it's not, then the goals have to be revised. Okay, so this is a totally unconventional approach to goal programming. I mean, unconventional approach to multi-objective optimization, which is not used by many people because they don't know this method. So first we will look at this goal programming with a simple linear programming problem. The first method is with inequality constraint, which is the easiest way. So in this case, we need to specify the maximum value with the objective function can attain. So suppose I have two objective functions, okay, to minimize stress or to minimize cost. So the stress must not exceed 500 MPa. So you have to find this value, 500 MPa as a goal. Then cost of production must not exceed 1000 rupees per unit. This is another goal. So first you have to fix these goals from practical experience. Okay. So now we will look at it with a simple linear programming problem because the textbook the topic of goal programming is very complex. So this method is very easy and you can understand easily. Suppose I have three objective functions, okay, and x and y are the two variables. So F1 is time of production must be minimized, then cost of transportation must be minimized, and machining cost must be minimized. Actually, it's not minimization. So in goal programming, we are not doing minimization or maximization. We are simply seeing if a goal can be attained. Okay. So it's not minimization or maximization. We'll see if F1 can reach a goal, F2 can reach a goal, and F3 can reach a goal. And it is subject to some usual constraints. So three objective functions are there. Okay, so suppose from previous experience, we know some reasonable goals to give the objective functions. I think this is the time of production. I think this is the first one. Okay, time of production. Okay, so we know that time of production should be less than or equal to 42 hours. Okay, from our previous experience. So we fix the goal for F1 as F1 should be 42 hours or less. Okay. Actually, in goal programming, strictly speaking, there's no minimization or maximization. The goal is to reach as close to 42 as possible. Okay. Goal attainment is the main objective of goal programming. Okay. So first we give a goal of 42 hours. So we write with the slack variable this equation. So S1 is a slack variable. S1 is greater than or equal to 0. So when S1 is equal to 0, our goal is attained. Because when S1 is equal to 0, then the time for transportation is exactly 42 hours. Okay, then 60 is, I don't know, what is 60? Cost of transportation. Cost of transportation, our goal is 60 rupees. Okay, and that goal is fixed from practical experience. Okay, so the inequality method, we have to write it as less than or equal to 60, and then we put a slack variable S2, such that S2 is greater than or equal to 0. So when S2 is equal to 0, our goal is exactly attained. So similarly for F3. So we define with slack variable S3, and S3 is equal to 0, the objective function 3 goal is exactly attained. So now what we do is that we rewrite the original problem like this. So now the new set of constraints are, okay, so these 3 new constraints will come. Okay, so F1 is equal to 42, F2 is equal to 60, F3 is equal to 40, then S1, S2, S3 is greater than or equal to 0, plus the old constraints. So now our objective function is to minimize S1 and S2 and S3. So you can minimize S1 and S2 and S3 by minimizing the sum of S1 and S2 and S3. Because S1, S2, S3 are all positive numbers. If you minimize S1 plus S2 plus S3, then each of this will try to become equal to 0. So now the original multi-objective optimization problem becomes a goal programming problem. Okay, goal programming problem. So now we can solve this in the MATLAB. Okay, so in the MATLAB LinProg, the same problem was solved. The answer is that x is equal to 6, y is equal to 0, S1 is equal to 0, S2 is equal to 0, S3 is equal to 10. So the goal for objective function F3 is not attained. So for F3, okay, 5x plus 4y plus S3 is equal to 0. Now S3 is 10. Okay, so 5x plus 4y is 30. Okay, so we are not able to reach 40 for the third objective function. You can only reach 30. Okay, so the attainable goal for the third objective function is 30 and not 40. Okay, so if you want, you can do this problem again by changing the goals. Okay, maybe 40, 50, 20. You can change the goals and run the problem again until all the 3 goals are attainable. So that is the goal programming method. Okay. Then goal programming with equality constraints. So in some cases, we want to set a goal exactly equal to some value. So in the last topic, we set the goal as less than or equal to something. Okay. If you want to put equality sign, then it becomes more complex. Then you have to add a positive deviation and negative deviation. So suppose F1 you are giving a goal of 10. F1, okay, so the goal is 10. So a positive deviation eta 1, negative deviation delta 1. So you have to minimize this eta 1 plus delta 1. So it will come closer from both sides, from top and bottom. So that is the main difference here. Okay, so this we need not look too much into it because it is not, this equality constraint method is not used much. Okay, so now so you have to minimize this thing, eta 1 plus delta 1, eta plus delta 2, eta 3 plus delta 3, etc. So because all these are positive values, when you minimize their sum, hopefully all these will become 0, 0, 0. Okay. So this is the equality constraint version of goal program. So this goal programming and all, it will not be asked for exam. Okay, but maybe just some theory question like what is goal programming, something like that. So then you can explain all these things. Okay. So no worked out examples will be asked with goal programming because obviously without MATLAB you cannot solve these things. Okay, so Now we reach the very important topic or multi-objective genetic algorithm. So in actual practice, nowadays, everybody will use only multi-objective genetic algorithm to solve the multi-objective problems. Nobody will use that epsilon cut method or the graphical method or weighted average method or those type of things. The multi-objective genetic algorithm are sometimes preferred over the analytical methods. So they are general purpose methods. They're applicable to linear or non-linear problems. And also, unlike the method of constraints, epsilon constraint, okay, unlike the method of epsilon constraint or weighted sum method, there is no need to know the internals of the problem. So what is the meaning of internals of the problem? So in this epsilon constraint method, first of all, you have to find the range of F2, and then you have to divide the range into different epsilon values. So you have to know the internals of the problem. You have to know the feasible region, what is the minimum value of F2, what is the maximum value of F2, and then you have to divide it into equal gaps of or different values of epsilon, etc. So that requires some human intervention. Okay, so all these things are not required in the genetic algorithm. It is like a black box. You just leave the problem to the genetic algorithm and it will slowly find the Pareto from after hundreds of iterations. The sample of existing genetic algorithms used for multi-objective optimization is presented here. So all these I have taken from this book, Multi-Objective Optimization from Kalyan Mohidev. So it is a very tough book, and I have simplified all the algorithms with some schematic diagrams. Okay, and out of this, many genetic algorithms I am going to show you. The most important one is NSGA2, which will be asked for the exam. Okay, NSGA2 will be shown in the end. Okay, only that is important for exam. You have to study the methodology of NSGA2. Okay, so how does the multi-objective genetic algorithm work? So first it will generate a population here. Okay, then it will do crossbreeding and mutation, and it will come here. So this is the next generation. Then it will do crossbreeding and mutation. It will come here. Okay. Okay, it will come like this, and finally it will attain the converged Pareto. So you know you have reached the converged Pareto front. There is no further improvement in the front after several iterations. That is if the F1, F2 values don't change after further iterations, it means that you have reached the converged Pareto front. So this will take like sometimes it will take 1 hour or 2 hours for the genetic algorithm to reach the converged Pareto. So first we are going to look at one of the earliest multi-objective genetic algorithm called vector evaluated genetic algorithm, or VEGA. This vector evaluated genetic algorithm is the earliest multi-objective genetic algorithm. I think it emerged in the 1980s or something. So it is a straightforward extension of single objective genetic algorithm logic to multi-objective genetic algorithm. So first a random population of N is created in the design space, or N XY points are created. So if there are M objective functions, the population is divided into M equal groups randomly. Okay, so suppose I have population of N. Okay, so n. Population of n is here, and three objective functions. So divided into group 1, group 2, group 3. Okay, so in this group 1, the population is arranged in the order of fitness of objective function F1. In group 2, the population is arranged in the order of fitness of objective function F2. And in group 3, it is arranged in the order of F3. Okay. Then the fittest members in each group are put into a common mating pool. Fittest members of each group are put into common mating pool. So that we'll see in the next slide. So from this common mating pool, crossover and mutation are done to create the next final population of N. So we'll see with a simple flow chart. Okay. Suppose we have three objective functions, F1, F2, F3. The population N is 18. So starting population N is 18. So now we have three sets, each made of 6 members. So what you do is that out of this N is equal to 18, you randomly pick 6 members and put it into set 1. Then you randomly pick another 6 and put them in set 2. Then you randomly pick another 6 and put them in set 3. Okay. So what you do is that, so this set 1 is now ranked based on objective function F1. Set 2 is ranked based on objective function F2. Set 3 is ranked based on objective function F3. Okay, so set 3 is, okay, so this set 1 is ranked like 1, 2, 3, 4, 5, 6. This is the best F1. This is worst F1. Then set 2, 1, 2, 3, 4, 5, 6. This is best F2. This is worst F2. Worst F2. Then set 3 is, 6 members are there. This is best F3. This is worst F3. Okay, then, the best 50% or 60% of each set is put into common mating pool. Okay. So now this common mating pool will have best parents from set 1, set 2, so set 1, set 2, set 3. So best parents from the point of view of F1, F2, and F3 are all put here. So now what you do is that you take 2 parents at random and do the crossover. Okay, 2 parents are picked like this at random. So you do the crossover until 18 offspring are got, 18 children are got. Okay, so now this 18 children will come here. Okay, 18 offspring will come here, and then they are again divided into set 1, set 2, set 3, etc. Then all members in the common mating pool are considered equally fit. Okay. So all members in this common mating pool are considered equally fit. The reason is that they belong to different objective functions. Okay, so this is just a closer look at set 1. Okay, so let us look at set 1 here. Okay, so set 1 will have say 6 members, 4, 5, 6. So they are ranked according to fitness of F1. So suppose our crossover pool is 60%. Then we take 4 out of 6 and it is put into this common mating pool. Okay. Okay, so this is for set 1 for best. Similarly, set 2 for. Similarly, set 3 4. So 4 plus 4 plus 4, 12. 12 members will be in this parent pool. Okay. Okay, so common mating pool will have 12 members. That is 4 from each set. All these members are considered equally fit. And crossover and mutation is done by randomly picking a parent with uniform probability. Okay, there's no Roulette-Wheel method here because all these F1, F2, F3 are different objective functions. So all these parents are picked up with equal probability. So what you do is that, okay, so parents are numbered from 1 to 12. You generate a random number between 1 and 2. Then you pick one parent. Then you generate another random number between 1 and 12, and you pick another parent. So that way you get 2 parents to cross over. Okay, the results of the crossover give the next generation of 18 members. And these 18 members are again grouped into 3 sets. And again the iteration starts. Okay, then comments on this Vega. So Vega is simple and easy to program. Actually, from what things I showed you in 2 slides, you can easily write the Vega program. It works reasonably well and gives the Pareto front. But Vega emphasizes solutions which are good for each individual objective function. So the Pareto front points obtained by Vega contain more points at the extreme than in the intermediate region. Okay. So there will be fewer points in the middle of the Pareto. Okay. So if you run for maybe a lot of iterations, you may get 1 or 2 points here, but the points will be bunching up at the ends. Okay. So that is the disadvantage of this vector evaluated genetic algorithm. Okay, we can stop now.
इधर तो